Now, as section 2, I would like to talk about TDR, which stands for Time Domain Reflectometry. Even when we call something a transmission line, there are cases where we do not know its internal structure. In other words, it may be a kind of black box. In that situation, we apply a step waveform to the line. Then, as we discussed before, a reflected wave comes back. From that response, we estimate what is connected at the end of the line and, more generally, what kind of structure the line has. That is the basic idea of TDR. As an example, consider a line of length L, terminated only by a purely resistive load R sub L. Let the normalized resistance be R tilde. Then at Z equals 0, the observed voltage is V of 0t, which we simply write as V of t. Using the formula from the previous section, we obtain V of t equals V0 of t plus gamma times V0 of t minus 2L over C. The first term is the incident step. The second term is the reflected wave, which travels to the load at Z equals L and then comes back to Z equals 0. So it appears after the round-trip delay, namely 2L over C. Here we assume that the source side is matched, so that further reflections at Z equals 0 are ignored. Assume that the incident step is normalized to amplitude 1, and also the velocity, c, and the characteristic impedance, Z0, are known. We observe this voltage with a digital oscilloscope. Take the horizontal axis as time t, and the vertical axis as the voltage at Z0. Then at first, the waveform rises to 1, which is the incident voltage step. Later, at time 2L over C, the reflected wave arrives, and the voltage changes again. The new level becomes 1 plus gamma. So from the amount of this second change, we can determine gamma. Once gamma is known, the load resistance can also be found, because gamma is related to the normalized resistance by gamma equals R tilde minus 1 divided by R tilde plus 1. Also, from the time when this second change appears, we can determine the location of the discontinuity. Since the propagation velocity c is known, the distance is given by L equals c times t sub r over 2, where t sub r is the reflection arrival time. So TDR is a method that tells us both where a discontinuity is located and what kind of termination or load is present. Let us look at several examples. First, consider an open circuit. In that case, R tilde goes to infinity, so gamma is 1. Therefore, a unit step is first observed as 1, and after the round-trip delay, the reflected wave adds in phase. So the voltage becomes 2. If we see that kind of waveform, we know that the far end is open. Second, consider a short circuit. Then the load resistance is 0, so gamma is minus 1. The reflected wave has opposite polarity, and it cancels the incident wave. As a result, a unit step first rises to 1, but after the round-trip delay, it returns to 0. Next, consider the case R sub L equals 2Z0. Then the normalized resistance is 2, so gamma is 1/3. If the input step has amplitude 1, the final level becomes 1 plus 1/3, that is 4/3. Similarly, if R sub L equals Z0 over 2, then the normalized resistance is 1/2, and gamma is minus 1/3. So the reflected wave is opposite in polarity, and the final level becomes 1 minus 1/3, which is 2/3. In this way, by looking at the TDR waveform, we can infer the resistive load connected at the termination. That is the essential idea of TDR.